Chapter 12. Hmm. Chapter 12. Systems of linear equations and inequalities in more than two variables. Section 12.1. Systems of linear equations in more than two variables. Okay, so this is really just a continuation of what we did back in Chapter 3. So in Chapter 3, we had systems of two linear equations and two variables. So suppose I have, instead of just ax plus by, suppose I have cz equaling d. And let's have another plane, ef g h I j k l. Okay, so this will be an example of a system of three simultaneous linear equations in three variables. A solution to the system will just be an ordered pair, such that when we place these numbers into, so that what that means is that all three of them must be satisfied. So if you plug in x, y, and z into each of these three equations, then they must solve each of them. They must make each of these three equations true. So let's recall sort of the techniques that we gave from last time, from chapter 3, for solving systems of linear equations. And these will basically be the same techniques that we're going to be using now. One was graphing. Well, in two simultaneous linear equations with two unknowns, two variables, it was really not a very good technique. Graphing, it was rather difficult to usually tell where things intersected. With three equations, or maybe four equations, or whatever, it's going to be much, much more difficult. Matter of fact, like nearly impossible to see where these actually intersect. But just like what we did in chapter 3, this is really not a technique for solution, but it is a technique to see what we are, the guiding principle of what we really want to do, but not really and to give us guidance for terminology and all that. But it's not really a technique that we're ever going to use for actually solving systems, especially of more than two variables. We also did substitution. Substitution can be used for, systems having more than two variables. But as you have more and more variables, and more equations, it becomes more and more difficult to use substitution. Not because it's um, necessarily an incorrect way of doing it. It just gets confusing. And so once you have more and more variables, it's more likely that you may make silly mistakes if you use substitution, unless the system is particularly nice. So I usually won't be using substitution unless they're really nice sort of systems that I'm trying to solve. The next one we did was elimination. And we'll mostly be using this. We'll almost exclusively be using elimination to do this. Next was the matrix methods. And we didn't really do any of the matrix methods back in chapter 3. And we're really not going to be doing matrix methods in this chapter. We'll give a quick little hint at what matrix methods are, but we will, this is really more of a technique for pre-calculus and above. We'll give a little hint at what it is, but we probably won't actually do anything with it. And the last thing is determinants. And we'll actually be using determinants to solve some systems. Okay, so just like so those are the 5 methods that we're going to be looking at, and really elimination is the only one we're going to be spending the majority of time doing. So just like in the previous chapter, we use the graphing technique to really just classify different types of solutions. So that's what I'm going to be doing now. So let me just do show you how to classify systems. Systems solutions. So just like in when we had the case of two linear equations in two variables, a solution was where they intersected. Well, we'll do this, except in this case, they're not going to be lines, but they're going to be planes. And so, if I'm talking about 3 equations and 3 unknowns, well, one of the equations will look like a plane in space. Another equation could look like another plane in space, and so they'll be intersecting along this line. And suppose you have another plane going in this direction. So suppose that they all 3 intersect at that point. Then that one point will be your solution. So in this case, this is the case of intersecting planes. 3 . Notice that there is just one solution. And so we'll be calling this a consistent system. Well, it's consistent and it's also independent. Okay. So this is the case, and of just having three planes that intersect just at one point. Now suppose you have the case where we have no solution, and so suppose I have, well, 1, 2, 3 planes, and they're each parallel to each other. And so this is the case of 3 planes. So maybe I'll label this as, this is the no solution case. Okay, so suppose we have 3 parallel planes. Okay. Then this will have no solution. And maybe I'll divide it there. But we can also have the case where, well, and let me separate this by a little. So suppose I have a plane and I have another parallel plane. So this will be the case where we have 2 parallel planes and I have another plane intersecting these. Then the intersection of this plane with this other plane is this line. The intersection of this plane with this plane is another line. But these 2 lines are parallel lines. And so there is no point where all 3 of these intersect. And so this is the case of 2 parallel planes. And again, they have no solution. And so we will call this an inconsistent. So for both of these cases above, this is an inconsistent, and of course independent system. Okay. So lastly, let's look at, the case where there's an infinite number of solutions. Okay. So this is a case of infinite number of solutions. Well, one case could be where I have one plane, then I have a second plane, which is coincident, and I have a third plane that's coincident. So they intersect along every place in this plane. Okay. And so they intersect everywhere along that plane. There it is. So let's say, actually I could make it bigger. They intersect everywhere along here. Okay. And so this is the case of 3 coincident planes. And so it intersects everywhere across at every point on the plane, because every point along the plane intersects the other 2 planes, because they're 3 coincident planes. And so this will have a 2-parameter family of solutions. Because for every point in the plane, well, there are 2 free parameters that will generate this plane. I can also look at the case where we have, say, one plane going this way, another plane going this way. So if they intersect along, let's say, this line, and then I have another plane going this way, which also intersects along this line. Okay, and so I have 3 planes intersecting along a line. This will generate, well, there's really only one free parameter. You're just going in. Sorry about that. You're really just going in this one direction here, either backwards or forwards. And so this has a 1-parameter family of solutions. It looks like a line, whereas above, this looked like a plane. And so these 2 cases here, we call this a dependent system. Okay, here, wait 1 second. Okay, I call these cases a dependent system. And of course, it's also consistent. We will have to determine the equations for the solution for each of these cases. So we'll have to find the equation of the plane in this case here, the equation of the line in this case. Oh, why is it 2? Because you can go and think of it if you if you are on the surface of a plane, you can go in 2 directions. You can go, north, you can go right, left, you can go, up, down, or whatever. So you can go in 2 directions, right? And so there are 2 parameters. So you can think of, say, if you're on a map, okay? So you can either go north or you can go east or the opposite, south, west, etc. Yeah, so that's why it's called 2 parameters. And in the other case, it's called 1 parameter because you can only go in 1 direction. You can either go forwards or, the opposite, backwards. But you can't go any other direction. You can just go in 1 direction. So it's 1 parameter. Okay, good. And so obviously this is for the case of, so notice for three equations, three unknowns, we had um, three different cases. We can either have no solution, the case of parallel planes. We can have one solution, the case of intersecting planes, or we can have um, an infinite number of solutions, the case where you have a coincident, somehow some coincidence occurring, where either you have coincident planes or they intersect along, say, some sort of subspace, along a line. Okay? So, of course, if you have four equations, four unknowns, then it's either 0, 1, or infinite number of solutions. But the infinite number of solutions could either, have zero, we could either have 1, 2, or 3 parameters, etc. They can have as many parameters, except for one less than the number of variables in the system. Okay, so let me do some equations, some examples. And so on page 400 and, no, 512, page 512. Let me do some examples. So in exercises 1 through 33, solve the system of equations. And so let me do each of these. Now, what you'll notice is that usually these aren't very difficult. The hardest part is just being sure you don't make any errors, because if you make any sort of error, it will anything you will not get the correct answer, and these are rather large systems, so it's easy to make a small little error. It's easy also to occasionally get lost when you're trying to do these. Okay, so let me do this. And let me call this first equation R1. So I'll label everything so hopefully we don't get lost. X minus y plus 2z equals -2. -2x plus 3y plus z equaling 5, or 3. -x plus y plus 3z equaling 2. Okay, so the first thing you're going to have to do is determine what variable you want to eliminate. And once you've done that, then you will be consistent and you will use every equation to eliminate every instant of that variable. So I can either eliminate x, there's a 1x, y, there's a 1y, or z, there's a 1z. Actually, in this case, x, y, or z is just as easy to solve for. So let me eliminate x. There's no real advantage because all the numbers are very similar, because you have a 1 in front of the x and small numbers in front of the other x's. You have a 1 in front of the y and small numbers in front of the y's. You have a 1 in front of the z and small numbers in front of the z. So it really doesn't matter which one I use. So let me eliminate x. Okay. So I will first use two equations to eliminate x from those equations. So let me add R1. Maybe I'll just write it here. And R3 minus x plus y plus 3z equaling 2 to eliminate x. So let's do that. So the x's cancel, the y's cancel, so that's really nice. And that usually doesn't occur. Equals 0. So now, if this occurs where you've eliminated several variables and there's only one variable left, I can solve for that variable. So this is an unusual case where everything becomes really nice and easy. So first, I find that z is equal to 0. Okay, good. Now, let's use R1 and R2 to determine y. So let's see, I have R1, and I want to multiply R1 by 2 because I want to eliminate x. So 2R1, which is 2x minus 2y. But notice that the z is 0, so I'm not even going to write that because I know anything times 0 is 0, equals negative 4. Okay. And let me write down R2. So R2 is minus 2x plus 3y plus z, but z is 0, so plus 0 equals 5. Let me add these together. X's cancel. I get 3y minus y, minus 2y, 1y, equals 1. Good. So far I figured out x and y. Now, all I have to do is figure out, so I figured out y and z. All I have to do now is figure out x. And I can use any of the three equations to figure out x. Maybe I'll just use the first equation. So let me use R1. To solve for x. So x minus y plus z equals negative 2. And so add 1 to both sides of your equation. So x is equal to negative 1. So my solution is the ordered pair negative 1, 1, 0. And that is the solution to my system. Usually, I just box x, y, and z and assume that you can determine what the other variables are, what the actual solution is, given that I've solved for x, y, and z. Okay. Let me do problem number 3. R1 x plus 2y minus 3z equals 0. R2 3x minus y plus z equals negative 7. R3 2x plus 5z equals negative 4. Okay, so the first thing that I notice here is that this third equation has no y term. And so that makes it particularly nice. So that means that if I can somehow eliminate y from the other equations, then I will be done with that step. And then I'll just have two equations and two unknowns. And so that's what I'm going to do. I'm just going to try to eliminate y from the system and then solve it. And that will give me a fast route to solve the system. Okay, so let's do that. So let's eliminate y. And so I'll take R1 and then I'll take 2R2 and I'll add these together. So if I do that, what I notice is that the y's are going to cancel. And so if I use that new equation along with the third equation, then I'll only have two equations and two unknowns. And that's quite preferable. Okay, so let's do this. So this is equal to 7x, y's cancel, minus z equals negative 14. I'll call this S1. And then I notice that, well, I'll call the third equation, I'll call R3 S2. And so if I do that, what I notice is that now I have two equations and two unknowns. And let me try to solve that. And that is something that we've done in the past. And so let's try to eliminate z. To eliminate z, I'm going to take 5 S1 35x minus 5z equals negative 70 and add that to S2, which is 2x plus 5z is negative 4. So I get 37x. The 5z's cancel, equals negative 74. Divide both sides of your equation by 37. And so I get here that x equals negative 2. And I'll just say, well, rather than writing it as an ordered pair, as I did above, I'll just box each of these answers and assume that you can figure out the ordered pair from there. Okay, so I've determined what x is. Okay, good. Now I can use that to determine z. Oh, maybe I'll use S1. Determine z. Please note that you can plug back, or I could have used R3. You can plug into any equation above, doesn't matter where, just so long as it is an equation. It's not an equation that only involves this one variable, so that at least it involves a your variable that you're substituting in, plus at least one additional variable, preferably just one additional variable. And so let's do that. So S1 is 7x minus z equals negative 14. Oh, so that's kind of nice. So negative 14 minus z is negative 14. Add 14 to both sides. So if you do that, you get negative z equals 0. Divide by negative 1. So z is 0. So I've solved for x and z. Now all I have to do is solve for y. Let's say we do it in the second equation. And so let's use R2. So R2 says 3x minus y plus z equals negative 7. So negative 6 minus y equals negative 7. Add 6 to both sides of your equation. So you get negative y equals negative 1. And so y is equal to 1. So I've determined x is negative 2, y is positive 1, and z is 0. And so I've solved the system of equations. Okay, so let me do problem number 5. Negative 4, oops, call this R1. Negative 4x plus 3y plus z equals 6. X minus y plus 7z equals negative 9. R3, 2x plus y minus 6z equals 5. Okay, so let me just check. Negative 4x plus 3y plus z equals 6. 1x minus 1y plus 7z equals negative 9. 2x plus 1y minus 6. Okay. That's negative 9 and 5. Okay, so let me do this. So I can either eliminate x, y, or z, and it seems to be easiest to eliminate y because there's a 1, 1, and a 3. So eliminate y. So first let me just add R2 plus R3. So x minus y plus 7z equals negative 9. 2x plus y minus 6z equals 5. So I can just add these. So when I do that, I get 3x plus z equals negative 4. Let me call this S1. Okay, so that's, now I have an equation with two variables. I've used R2 and R3, so I need to use R1. Let's use R1. I want to eliminate y. R1 and R2 then. And so let's do R1, negative 4x, 3y plus z equals 6, and 3R2. 3x minus 3y plus 21z equals minus 27. So let's do that. So if I add these together, I get negative x plus 22z equals negative 21. Okay. Call this S2. Okay, so I want to eliminate, let's say, so I have S1 and S2. So that's a system of two equations and two unknowns. And so I want to eliminate, let's say, x. Question. How I got 3R2. Okay, so let me rewrite S1 and S2. So S1, I forgot what you were asking. 3R2. Okay. So let me write down R1 and R2. So R1 was negative 4 plus 3 plus 6, and R2 was x minus y plus 7z equals negative 9. Okay, so what I could do here is if I want to eliminate the y, I take whatever number's here, put it there. Whatever number is here, I multiply that. So this was a 1, so I multiply this guy by 1. This was a 3, so I multiply this guy by 3. Because if you do that, then you notice I multiply 1 times 3 and 3 times 1. So that means that these guys are going to be eliminated, so long as these numbers here, these signs are opposite. And so that's what I did. So I said, look, this, maybe I'll go to the top. This had a 3, so I multiplied this guy by 3. This had a 1, so I multiplied this guy by 1. The signs are opposite, so I can just make each of these positive. If I do that and I add them together, then the y's will be eliminated. It's the same way we did it when we were dealing with two equations and two unknowns. Just looks a little different because it's 3 equations, but it's the same technique. Okay, so I wanted to eliminate x from S1 and S2. So S1 is 3x plus y equals negative 4. Okay. S2 is a minus x. So I'm going to multiply this by 3, because there's a 3 here. And I'm going to multiply this guy here by a 1, because there's a 1 in front of this x. So minus 3x plus 66z equals negative 63. Okay. Let's add these. So I get 67z equals negative 67. So divide by 67. So I get z equals negative 1. Okay. So I found that, I've only solved for z. So I found that z is negative 1. Let me determine x. So I can just use this equation here to determine x. And so I have determine x. Actually, I'll use this equation to determine x. So S2 says negative x plus 22 times negative 1 equals negative 21. So add 22 to both sides of your equation. So I have negative x equals 1. And so divide by negative 1, so x is equal to 1. X is equal to negative 1. Let's determine y. Maybe I'll use the third equation, R3. So let's use R3. Which says 2x plus y minus 6z minus 6z equals 5. Okay, so I get negative 2 plus y plus 6 equals 5. So y plus 4 is 5. Subtract 4 from both sides. So I get that y is equal to 1. Okay, good. So in this case, x is negative 1, y is positive 1, and z is negative 1. Any questions about that? Okay. Let's do problem number 7. Three x plus y plus z equals negative 2. Oh, and I guess I should say, especially on an exam, what you should do is at the end, plug these three numbers in to each equation and see if it works. That will give you an idea if it's correct. It's not 100%. It's not 100% guarantee, however, because if there's an infinite number of solutions, you may have just found one solution, whereas there's an infinite number of solutions, not just one. But at least it gives you a hint that maybe you are doing it correct. R2 x plus, we're doing 7, it's 2y plus 3z equals 0. So 3x plus y plus z is negative 2. X plus 2y plus 3z, 0. And R3, 2x plus z equals negative 3. So again, I noticed that there's no y in this third equation. So let's eliminate y from the first two equations. So let's do negative 2 R1, because there's a 2 here. So I'll put the 2 in front. There's a 1 here. I'll put a 1 in front. Since the signs are the same, I've got to change one of them. So I might as well just change the R1. So negative 6x minus 2y minus 2z equals 4. And I'm going to add to that R2, which is x, 2y, 3z, 0. So let me do that. And so I get negative 5x plus z is 4. Let's call this S1, and I'll call R3 S2. And let's eliminate z, since there's 1's in front of these. So I'll take negative S1, 5x minus z equals negative 4, and take S2, 2x plus z equals negative 3. Add them. So you get 7x equals negative 7. Divide by 7. X equals negative 1. I can figure out what z is. Let's just do S2. I have 2x plus z is negative 3. So I've got negative 2 plus z. So let's add 2 to both sides of my equation to get rid of the 2. So I get z equals negative 1. Okay. And let's figure out y. I guess I'll use the first equation for y. So 3x plus y plus z is negative 2. So negative 3 plus y minus 1 is negative 2. So y minus 4 is negative 2. So add 4 to both sides of your equation. So y is equal to 2. Okay. Let's do problem number 9. So I have y minus 2z is negative 8. X plus z equals 4. I have 2x minus y is equal to negative 4. Okay, so let's eliminate one of the variables. Maybe I will eliminate y. And so then I'll use the fact that there's no y here. Okay, so eliminate y. So I have R1 y minus 2z negative 8. I have R2 2x minus y equals negative 4. Add these together, and so I get 2x, y's cancel, minus 2z equals negative 12. Let's divide everything by 2 so it looks nicer. So I have x minus z equals negative 6. Call that S1. I also have R2, so I'll call that S2. Is just x plus y plus z equals 4. So let's eliminate z. Let's just add these together. So I get 2x is equal to negative 2. Divide by 2. So x is -1. Let's use S2 to figure out z. So I have x plus z is 4. Add 1 to both sides of your equation. So z is 5. I have x and z. Let's determine y. So let's use the first equation, R1, to determine y. So I have y minus 2z equal -8. And so add 10 to both sides of your equation. And so I just have that y is equal to 2. So x is -1, y is 2, and z is 5. By the way, each of these are the cases of, and maybe I should say that here. Well, I'll put it on the side. Each of these here are consistent systems. These are the cases of intersecting lines. Or I'm sorry, this is 3. So intersecting planes. Okay, let's do problem number 11. Two x minus y plus z equals 6. 3x minus y plus z equals 6. 4x minus 2y plus z plus 2z equals 12. A lot of things are going to cancel there. Okay, so let's try to eliminate z. So I'll just take negative r1 plus r2 oops, that's a 3x minus y plus z equals 6. And let's add these together. So I get x, the y's, z's cancel, equals 0. So I've solved it. So I found that x is 0. But now, let me rewrite this where you can now see what's happening. So let's look at R1. R1 now becomes negative y plus z equals 6. R2, 3 times 0 is still 0, becomes negative y plus z equals 6. These are the same equations. And then let's look at R3. which is equal to 0x, so 4 times 0 is 0, minus 2y plus 2z equals 12. But then that says, but then notice, R1 is the same as R2. And so that means that really these two equations are the same. So, I just rewrote them twice. So really, I was kind of stupid. I should have just written them once. So I can really just eliminate R2. So just eliminate R2. Because we wrote it twice. But notice that R3 is just equal to 2R1. So R2 is the same as R1, but R3 is just twice R2. So really, it's just R2. If you just multiply, well, maybe what I'll do is I'll just actually eliminate these, and you'll see what happens. So really, all these three are the same. So if I take, and maybe I'll call them S's rather than R's, just so you can, I plugged in 0 for X. So I'll call them S1, S2, S3. Notice that S1 minus S2 X's, Y's cancel. 6 minus 6 is 0. And so you get 0 equals 0. Ooh. So that means that one of the equations can be eliminated. But then, so that means that these are coincident sort of things that are intersecting. Then I look at, let's look at 2 minus 2, S1, which is 2y minus 2z equals negative 12. Look at S3, add that, which is negative 2y plus 2z equals 12. Again, I get 0 equals 0. So that means that these three equations, well, they're all the same lines. They're all coincident. Okay, and so that means that I only really have minus y plus z equals 6. So let's add y to both sides of my equation. So that says that z is equal to y plus 6. And z and y is free to vary. Oh, so it's a free parameter. It's a one parameter family of solutions. And so usually, and I'll write it as an ordered pair, I'll let y equal, I don't know, call it some other variable. Usually they use Greek letters, but I'll use something like k. Let y equal k. Then my solution is, well, x is always 0. Y we called k. And well, z is y plus 1. And so I'll just call it 6 plus k. And this is my one parameter family solutions. Well, maybe I'll write it up here. So this is for any k, which is real. This is a one parameter family of solutions. So this is the dependent case. So this is a dependent system. Oh. So you know that it's not independent. Well, it could either so you know it's not intersecting lines. If 0 equals 0, if you have a case where it's a number equals a number, then I know it's not intersecting planes. It could either be a dependent system or an inconsistent system, because 0 equals 0 usually means there's infinite number of solutions, unless you go further down and another one of the equations, when you simplify it, becomes something that's a false statement, like 0 equals 1. But usually 0 equals 0 does give you a dependent system, except when it doesn't. Okay, let me do problem number 13. Any questions about this? Okay. 13. Three x y z 5 x 2y 3z 4 or 3 13 2x minus y minus z equals 3. They all look pretty similar, but I think the y is easiest. So y is easiest to eliminate, just barely, but it's still. So let's eliminate y. So let's first do r1 plus r3, 3x plus y, 2z, 5. Let's add that to r3. 2x minus y minus z equals 3. And so if I add that, I get 5x plus z equals 8. Call this S1. Let's use maybe R2 and R3. Yeah, R2 and R3. So let's do R2, x plus 2y plus 3z equals 4. Let's do R2, R3, since you have a 2 here. So I have 4x minus 2y minus 2z equals 6. Let's add these, so you get 5x, y's cancel, plus z equaling 10. Okay, so that's S2. Okay, so now let's eliminate z. And so I'll do minus S1 minus 5x minus z equals negative 8 plus S2, 5x plus z equals 10. X's cancel, z's cancel, so you get 0, equals 2. But once you see this, you immediately know that this is a false statement. Since this is a false statement, I immediately know that this is a inconsistent system. And so this is the case of somehow parallel planes or whatever, but or parallel lines where, you know, but so you have either two or three parallel planes. Um, they don't all intersect at the same place. And so you know that immediately this has no solution. So you don't have to go any further because there's no solution to this system. It's inconsistent. So you're done. Any questions about that? Okay, 15. Is underdetermined system. Okay, so problem 15. In general, underdetermined systems will have a lot of solutions. And so R1, x plus y minus z equals 1. R2, 2x minus y plus 7z equals 2. So this is called an underdetermined system. Because there are only two equations, but there are three unknowns. So there are fewer equations than unknowns. If that occurs, we call it an underdetermined system. If there are more equations than unknown, we call that overdetermined system. In general, underdetermined systems have an infinite number of solutions. And so we'll see what happens here. Notice in this case, I can eliminate y by just adding these two equations together. So I get 3x plus 6z equaling 3. But that's all I can really do. I can divide by 3. But notice I've used these two equations to eliminate one variable, and I don't have any more equations left to deal with. So all I can say is, well, let's subtract 2z from both sides. So I have x is equal to 1 minus 2z. Okay, so I can let, let's say z equal k. For every real number k. Notice that there is, there'll be one parameter. The one parameter is going to be k. And we'll see that in the system in a second. So this turns out to be a dependent system. Because there's some free variables involved here. So that's what x is. Let's figure out y. Well, let's use our 1 to figure out y. I have x, which is 1 minus 2z, plus y, and maybe I'll call, since z is k, maybe I'll call it k. Minus z, which we call k, is equal to 1. And so I have 1 minus 3k plus y is 1. Subtract 1, add 3k to both sides of your equation. So I have that y equals 3k. So my solution looks like the ordered pair x. Remember, I'm letting z equal k. Y, which I called 3k, and z, which I called k. And so this is a one parameter family of solutions. So notice I have an infinite number of solutions, and they're different because I can take k to be anything. So for any real number k. And so it is a line in 3 space. And so there's some line in 3 space looking like this, which solves the given system of equations. Let's do problem numbers. Any questions about this? Let me do problem number 17. X minus 2y plus 3z equals 2. 2x 3y minus z equals 4. Actually, let me eliminate y. Not because, so notice again, this is underdetermined system. Okay. Let me eliminate y, not because it's easiest to do, but because it's better to show you. It's a good way to show you how to do this. What I was doing above. So let's eliminate y. Okay, so and maybe I'll put it over here because I don't have space. So I notice I have a 2 in front of this y. I'll put it the 2 here, a 3 in front of this y, so I'll put the 3 here. So I have a 3 R1 and I have a 2 R2. Notice that one has a negative sign, the other a positive sign. Since they differ in signs, I can just put a plus in front of both of these. Now, if these numbers, think of them sort of like a fraction. And so if there were things if this was like say a 6 here and a 4 there, then you'd put, say this is 6 here, you put a 6 here, a 4 here, you put a 4 there. But then you could reduce it, like 6 over 4. You could say, well, that's 3 over 2. So if there's some common factor here, you would reduce it, because it'd make it an easier sort of common multiple. Okay, so let's add these. 3x plus 4x is 7x. The y's cancel. Plus 7z equals 14. Let's divide everything by 7. So you get x plus z equals 2. Okay, good. But I've used 2 equations and 2 unknowns. I've used 2 equations There are no more equations I can use. So let's just let z equal k. Then this equation, maybe I'll call it S1, becomes x plus z equals 2. And so subtracting k from both sides, you get x equals 2 minus k. Let's determine y. None of them is easy. Let's do, oh, I see, because that's, if I would have let it be a 3k, it'd actually be better, because then, well, we'll have fractions, but, okay. So let me look at R2. And so from R2, I have 2x plus 3y minus z equals 4. Okay, so let's simplify this. So I have 4 minus 2k plus 3y minus k equals 4. Combine like terms, so I have 4 minus 3k plus 3y equals 4. Subtract 4, add 3k to both sides of your equation. And so 3y is equal to 3k. Divide both sides of your equation by 3. So y equals k. Okay. And so my solution is x, y, z. And again, this is for any real k. And so this is my one parameter family of solutions. So again, this is a dependent system. You have an infinite number of solutions. And so this is my one parameter family of solutions. Let me do problem number 19. 19. Is that really the time? 19. Oh, I have 54 to go. I'm not even close to being done. Okay. And these are going to be longer problems. Okay, so yeah, it ends at 1 o'clock. Okay, so I guess that's it for today, and we'll continue this tomorrow because it's going to take a while to finish off all these problems because they're a little longer problems. Okay?